Narayan is a PhD student working with Omar Magana, who's our quantum optics experimentalist at LSU, and he's going to tell us about his recent work that he posted with Omar and many others to the archive. Take it away.
Thank you so much, Mark. Thank you so much for providing me this opportunity to speak. Hello, everyone. I'm Narayan from Louisiana State University. Today, I'm going to be talking about spatial mode correction of single photons using machine learning. My presentation is mainly based on the archive preprint that we posted like 2 months ago. If anyone is interested, you can just use the reference number given here to access the paper, to access the archive preprint. And mainly, this project is mainly about the OAM modes of light. So let me briefly start with the introduction. Okay, let me briefly start with the introduction, what OAM is. As we all know, OAM stands for orbital angular momentum. As we all know, light not only carries energy for photon, it also carries momentum, which is evident from the fact that it exerts radiation pressure when it is incident on any surface. So basically, I'm focusing myself here on angular momentum part. There are two types of angular momentums. Light carries spin angular momentum and orbital angular momentum. Whenever spin angular momentum is basically associated with the polarization property of the light. Whenever we prepare light in right circularly polarized mode, it contains each photon in such a beam carry plus h bar spin angular momentum. Similarly, if it is left circularly polarized, each photon in such a beam carry minus h bar spin angular momentum. So that's one of the degree of freedom that has been used to encode quantum information. Today, I'm going to be mainly talking about orbital angular momentum. This is another dimension that has been used in use from several decades to encode the quantum information. So what happens is when you prepare a beam, when you prepare a phase structure of the beam in such a way that it is helically phased as it propagates, then what happens is the local pointing vector in such a beam is twisted around the propagation axis of the actual propagation of the beam. So in such a beam, each photon carry orbital angular momentum of the value defined by L(h bar). L is the OAM quantum number. So these quantities are like well quantized. So it has been used in many ways to encode quantum information in multiple technologies. I'll talk about that in the next few slides. So as I already mentioned, spin angular momentum is associated with the polarization of light. Similarly, orbital angular momentum is associated with the spatial profile of the beam. Most popular choice in quantum photonics to encode quantum information is Laguerre-Gaussian modes, which are solutions to the paraxial wave equation. And the characteristic features of such beams are helical phase profile and unique intensity structure. And these beams are basically defined by two quantum numbers, L and P. L is called azimuthal quantum number and P is called radial quantum number. So these two quantities basically define the phase structure and the intensity profile of such a beam. So using these quantum numbers, basically we can encode quantum information. This is a new dimension for encoding the quantum information in short. So when it comes to the generation, like how do we generate such a beam? So there are like multiple ways to generate this kind of beams, and there are multiple ways to encode orbital angular momentum in each photons of the light. These two are the most common ones that we use. The first one is using the spiral phase plate. So what happens is like you have a Gaussian beam, so this kind of phase profile. As it passes through the spiral phase plate, like spiral phase plate is built such a way that it makes if it makes like 1 pi turn, that's L equals to 1. If it makes like 2 pi turn, that is L equals to 2 encoding basically. So For each OAM value, like you have to fabricate a different spiral phase plate to be able to encode quantum information in the spatial mode of the beam. So, so that's one of the limitations of spiral phase plate. So that's why it's not very popularly used choice basically. That's why we have been using this another method using spatial light modulator. So what happens here is this is like a display. This is like a basically it's like a monitor, and each pixel in the monitor defines the phase shift amount. So what we do is we prepare this kind of phase structure, and it is combined with the diffraction grating, and you get this fork hologram. And such a fork hologram creates encodes these whatever the desired number of desired orbital angular momentum value is like you get that beam in first diffraction order. So in experiment, like what we do is you start with a Gaussian beam and you allow it to incident on the spatial light modulator that is displaying such fork structure. Then you get the OEM value that you intended to encode in the first diffraction order, and we basically put a filter to select that diffraction order. This is the most popular method because spatial light modulator can be controlled through a computer program. It can be changed dynamically. The current refresh rate of these spatial light modulator is like 60 hertz. Basically, you can change 60 different spatial modes in 1 second. So that's why it's very popular. It's the most preferred method in quantum photonics to encode the orbital angular momentum of the light. This is basically the new degree of freedom to encode the quantum information. So in case of, while trying to use other degrees of freedom like polarization and spin magnetic moment, like you're restricted in the dimension of the Hilbert space. Basically your Hilbert space dimension is 2-dimensional and you can only prepare a qubit. So you cannot go to a higher dimension. That's why OAM is important here, because in case of OAM, you can theoretically encode, you can theoretically access infinite dimensional Hilbert space. So you can see, you can prepare your qubit in any kind of, higher superposition of OAM modes. So what's the importance? Like when you're trying to encode, when you're trying to, from the quantum information perspective, like when you're trying to encode the information, the amount of information that you can encode is given by, basically restricted by the dimension of Hilbert space. So 8-dimensional OAM qubit is basically equivalent to 3 qubits in polarization basis. That's why it's really important, because it opens up the possibility of encoding multiple bits of information in a single photon. And another nice property about these, OAM modes or LG modes in general is that it forms a complete orthonormal set. So which makes it easier to do the projective measurements, and it makes our task a lot easier because of this orthonormality. And the meaning of meaning of a complete set is basically, I think we already know, but I'll just describe in short. The meaning of having a complete set is basically you can define any kind of spatial mode in terms of these OAM modes. Like you can define any spatial mode in terms of some linear combination of OAM modes. That's one of the important properties of these modes, and that's why it's very useful in multiple quantum technologies. So in 2014, Robert Boyd, they published one paper where they do quantum cryptography using high-dimensional twisted photons. What they do is they use these higher dimensional OAM states to encode to produce the encryption key and transmit it to Bob, and they do it like very efficiently. There's some error correction algorithm also they use in that, but basically they were able to show this kind of encryption and decryption successfully, and they were able to utilize this property of encoding multiple bits of information per photon. They were able to get up to 2.05 bits per photon, and then because of the higher because of the reason that the photons prepared in OAM modes live in the higher dimensional Hilbert space. It's more secure against the eavesdropping attacks. So that's one of the importances while trying to use it in quantum cryptography. And the most popular application of these OAM modes is optical communication. There are like basically two scenarios people have been using in optical communication. One is free space optical communication, and another is underwater optical communication. So in this paper, they show that the communication protocol in 1.6 kilometer distance in free space, and here they show underwater using some multiplexing and demultiplexing mechanisms in underwater communication. So basically, multiplexing means you can send multiple OAM beams coaxially in. You can combine these multiple beams in such a way that you can send it coaxially to the receiver from the transmitter in presence of like they also consider all of these scattering water currents and turbulence in their paper. So it has been shown in multiple, optical communication schemes. So it's kind of important from that perspective also. So what's really a problem? Like I already talked about what are the important features of using OAM degree of freedom. So let's talk about what are the problems like. So when you're trying to use OAM degree of freedom to encode quantum information, you have to rely on the free space transmission of the beams. Because if you try to propagate the beams using the fiber optic, basically what happens is you destroy the spatial mode, you collapse the spatial mode to the Gaussian, and you lost all the information encoded in it. So you cannot use fiber optics, but there are some exceptions, like people are working on designing special multi-mode fibers that can be used to transmit these kind of OAM modes, but those are very limited because one kind of one fiber optics can be used for just one value of orbital angular momentum. It's very limited. So that's why mostly to be able to utilize nice properties of these OAM beams in multiple technologies I just talked about, you have to rely on free space transmission of the beams. And in free space, what happens is like you have a lot of these molecules flying around, and there's a wind current, and that basically what that does is like it induces inhomogeneity in temperature and pressure of the medium, which randomly modulates the index of refraction. So that induces the random phase shift in the beam. So that destroys the helical beam profile, helical phase profile of the OAM modes. So that's where your information is encoded, and because of this inhomogeneity and these random fluctuations, you lose like either partly or completely the information encoded in such a beams. So that's why this is like one of the biggest hurdles while trying to use these modes in multiple technologies. That's why people are trying to come up with different solutions. Like conventionally, people have been using adaptive optics and the deformable mirrors to correct for this kind of effect. But those processes are very slow, and they are not very effective. That's why we are trying to find out a different avenue to explore what we can do to solve this problem. So whenever you see this kind of phase distortion in the OAM modes, like what happens is it induces a lot of mode crosstalk. Basically, what that means is like you started with a beam of let's say L equals to 5, then it scatters into different other OAM modes of in the vicinity of L equals to 5 basically. So when you are trying to do the projective measurement on the OAM mode that was originally sent, you like end up detecting the mode in some other OAM value. So that degrades the information that you sent. So that basically means like if you consider the free space as a channel, then it reduces the channel capacity. And also like if you're relying on OAM entanglement and you're propagating through the free space, then it also damages the entanglement. So that's also important considerations when you are trying to use some quantum properties in OAM degree of freedom. Fortunately, there's a way to simulate this effect experimentally inside the lab. So you don't need to really, go outside and set up these, sender and receiver turbulence to be, to actually perform the experiment, because we have a very good statistics that can model these random modulations in phase. So which is called Kolmogorov statistics, and we use these equations to basically uh, calculate the phase modulation that would have been induced if it was propagating in the free space. This R naught, it's called Fritz parameter. This gives the strength of the turbulence, and it is expressed in terms of another quantity called CN2. CN2 is called standard refractive index, and Z is the propagation distance. So we use in our experiment, in our project, we use the CN2 quantity to quantify how much turbulence is present in a particular phase mask. That's the quantity we use to quantify the strength. So this is our experimental setup. So in here, I have two experiments, basically one with a classical source and another with SPDC source. The first, we do the experiment with helium neon laser, 633 nanometer. So we filter the beam using single mode fiber. Out of this fiber, you basically get the nice Gaussian beam, and it hits the spatial light modulator, as I briefly talked about in previous slide, how we use a spatial light modulator to encode these OAM values in the beam. And this basically, the function of this spatial light modulator is to encode the particular value of OAM in the beam. And these, you can see like a lot of lenses and mirrors. Those are, not that interesting part of the experiment, but we need them. Like these are very important to filter the beam. Here we use this 4F system to filter the beam coming out of the SLM. SLM is basically sending out the beam in different diffraction orders, and we pick first diffraction order using this iris and send it to passes through a turbulent channel where it meets the random phase modulation. And another, I have the second spatial light modulator here, which is used by Bob to make the projective measurements on the qubits that were, the spatial qubits that were sent originally. That's the function of the second SLM, and it's also used to correct for the turbulence that was induced in this turbulent channel. So what we are doing here is basically, after passing through the turbulent channel, these beams get distorted, and we record like thousands of these beams using this expensive camera. This is like 70,000 camera. This can operate at the single photon level, and we use this camera to get a lot of like thousands of images that will be used to train the machine learning algorithm right here. And this machine learning algorithm first finds the strength of turbulence, and then there is another part in this computational algorithm, which is a gradient descent optimizer, which is used to optimize the phase mask. So basically finding the optimal at that strength, like for any strength of turbulence, like you have thousands of realizations. So we are basically trying to find what's the optimal realization of the phase mask that represents the turbulence that represents the turbulence that it went through. So basically that's the function of GDO here. And using a combination of this GDO algorithm and CNN, we produce a phase mask that will predict what the turbulence was here, and we basically revert the process, revert the effect of turbulence by encoding additional phase mask in the second SLM here. So that's how we perform the experiment. And first, using classical source, we characterize the channel, and we know that like what kind of turbulence exists in the channel. And after that, what we do is we turn off this laser and start the second laser that pumps the PPKTP crystal, and it produces a pair of photons which are entangled, and basically we're utilizing the temporal correlation of those two twin photons. So these are prepared in different orthogonal polarization. That's why we use PBS to separate those two photons. Like one of the pair of photons like goes to APD, it generates electrical signal in response to each of the photons arriving at APD. APD is a single photon detector. It's like it is a bucket detector based on this is just a avalanche photodiode. So electrical signal generated by this APD is sent to this ICCD camera, so intensified CCD camera. What that does is, like, whenever you see the signal from APD, it opens the shutter of the camera, and other times, like, the shutter of the camera is closed. So what that does is that increases the signal to noise ratio in the image, so that we can see the images at the single photon level. And another pair of another photon generated at the same time passes through this long coil of fiber, because there is an internal delay related to the camera. As electrical pulse arrives at the camera, there is an internal delay of 120 seconds that we need to account for in order for us to detect that particular photon at the camera whenever this electrical signal hits the camera. So that's the purpose of this delay that we are using in our experiment. So that's how we get the single photon images. And after we characterize using the classical laser, we perform the experiment at single photon level. I will show some of the results we have using the at the single photon level, as well as at the classical limit, basically meaning a high intensity limit. So the second part, this is the computational algorithm. So it's shown here. This is 5-layer convolutional neural network, nothing new. It's a simple algorithm. And I won't go into much detail about this right now. So these are the results at 3 different stages of our experiment. The first image is, this represents the OAM qubit or spatial qubit without any turbulence. And after it passes through this amount of turbulence, this is 80 CN2 value. It's the unit of this quantity is millimeter power minus 2/3. That's the unit I'm using. So after it passes through this amount of turbulence, like, the beam gets distorted, and after we apply, it passes after we apply the machine learning algorithm to generate the face mask to correct for the turbulence, we get almost whatever we started with. So it's not 100%, but we get very close to 100%. You can see these red beams are at the classical using the classical laser, and then this grayscale images are for the single photon cases. And we can see this is just L equals to 3 mode, and it passes through this amount of turbulence, and it gets like as I already mentioned, as I already showed in one of the slides, that at single photon level, the effect of turbulence is it's very bad. So that's why you can see the difference. Even with the 40 turbulence strength, the distortion is pretty bad. And after correcting for it, we get like almost what we started with. And this is just a different LG mode we performed the experiment on, and then we almost get back what we started with, except for the fact that I don't have like a lot of photons hitting here. Maybe that's because of the heating of the camera as we operated for a long time. Basically, I have to wait for a long time to accumulate like a lot of photons, and this camera has to be cooled at like minus 25 degrees centigrade. So after I operate for a long time, like, it gets heated. As temperature goes up, the efficiency of the camera goes down. So that's why you kind of see less intensity at the third image. So in order to quantify the performance of our scheme, I have I reconstruct these correlation matrices. This is without any turbulence, and this is with the turbulence, and this is after correcting for the turbulence. So the first one, like what I'm doing here, let me talk about how we get this correlation matrices. Like, first we send like particular OAM mode from Alice, and whenever Bob performs the projective measurement on that, like whatever whatever the mode the Bob finds that sent mode at, that's the probability it's shown here. Because of the size of the core of the fiber that we are using in our experiment, like we are limited by that. So that's why you see a little bit of spread. Like, it's ideally it's supposed to be a chronicle delta. Basically, ideally it's supposed to be identity matrix, but experimentally it doesn't happen because of the size of the core of the fiber. And like, even if you decrease your size of the core of the fiber, you have to be very accurate in terms of alignment. So there is a trade-off between that size and the alignment mismatch. So that's why it's really hard to get the perfect identity matrix. This is what we get without turbulence. And at turbulence, like it's almost impossible to identify what was originally sent. So that's the point we are trying to highlight here. And after applying the turbulence correction, we almost get back what we started with this correlation matrix. So in next slide, this is the normalized mutual information. We calculate this to quantify the channel capacity of our free space channel. Here, I just calculate the bits per photon, like the amount of information that has been exchanged between Alice and Bob per photon based on like the dimension of Hilbert space that I use. So you can clearly see in presence of turbulence, like the channel capacity goes down by a lot, and then after applying the turbulence correction, the improvement is like more than 100%. So that's really good thing. And then it almost approaches the case where I don't have any turbulence. So that's the important thing I wanted to highlight here. And this is how we quantify the efficacy of our turbulence correction protocol. We also perform OEM state tomography to evaluate the performance of our scheme. So this is the OEM qubit that we prepare. In our case, like I don't really start with any phase, this phi A0, and I use a 50-50 superposition. That means this quantity is 1 over square root 2. So to do that, to do the OEM state tomography, what I have to do is basically project the spatial qubit or OEM qubit that I started with on these six different bases, and then find the amplitudes of the projection, and that's basically used to reconstruct the real and imaginary part of the density matrices. And this is the density matrix without any turbulence, and this is the density matrix in presence of turbulence. You can clearly see it's supposed to be like all of these values are supposed to be 0.5, and the imaginary part is supposed to be 0 ideally, but that doesn't happen in experiment because of some experimental errors. Like even in case of no turbulence, like you see some small values of this imaginary imaginary row, but ideally that shouldn't happen. And in case of turbulence, like it's completely destroyed, and then you can see like large imaginary part of the density matrix also, like, and then these values are also skewed in presence of turbulence. So that's the point of this project. Like we are trying to get back the sanctity of the qubit, spatial qubit that we prepared. After applying the turbulence correction, this is what happens. Like we almost get back the qubit what we started with, and the fidelity between no turbulence and the turbulence corrected case is about 99.8%. This is the equation that I used to calculate the fidelity. In conclusion, OEM degree of freedom is very useful in multiple technologies, and the biggest thing, biggest limitation is it requires free space propagation, which is highly susceptible to the phase distortion, such as turbulence. And in the past, conventional algorithms like adaptive optics using like deformable mirrors, those have been used in the past. The drawback of using those methods is speed and performance, is not as good as using the machine learning algorithm, and the speed is very slow, so that we cannot really rely on adaptive optics to perform the turbulence correction at real time, because the turbulence is a dynamic thing, and you have to be very fast in order to catch up with the time. And we use a machine learning algorithm. It's very useful because it performs good, and it's very convenient in terms of speed also compared to the adaptive optics. And it opens up the possibility to implement these protocols in real time because of the speed, because the amount of time it takes to predict the correction phase mask for the turbulence in our case was like 200 millisecond, as far as I remember. that's pretty fast. So that's why it opens up the possibility to implement this protocol in real time. And these are the future directions that we want to explore in the future. Like we want to implement a real-time turbulence correction protocol, and we want to perform the QKD in presence of real noise or phase distortions. And also, like, we want to explore the possibility to extend this to the multi-particle states. Like in this case, like, I'm just using a bucket detector and, weak single photon source. Basically what I'm doing is I'm projecting onto the singles in the two-mode squeeze vacuum. But now we have, like, very high intensity single photon source. Maybe we can extend this, idea to multi-particle states also. So that's the, directions we are exploring this project too. That's all I have. Thank you.
All right, thanks, Narayan, for the talk. We actually hit the time of 1:45. So I think we should move along to keep on track. I do have some questions for you, but I'll write to you an email about them.
Okay.